Okay, everybody, so there's gonna be a little noise because they're doing something out in the hallway. Let me get back to our stuff. Hold on a second. One sec, okay. So we're looking at adiabatic compression. Okay. So we see that this quantity VT time to the F over 2 is a constant. Wow, that's very noisy. I hope you can hear me. Okay. All right. So let's see. Let's kind of rework this equation. I'm going to get another layer. Move this. I've got a Zoom thing right in my way, so you can't see it, I don't think, but I'm going to move it. Go away, Zoom thing. Okay. All right. Okay, so we have the VT, remember this is volume, T to the F over 2 equal a constant. Okay. Okay, but we know, right, that we can rewrite what T is, right? So from PV equals NKT, we can rewrite T is PV over NK. Okay, so let's substitute that in here. V, and then we have our T, and that's going to be PV over NK. K, and that's all to the F over 2 equal a constant. Okay. And now we are going to take the F over 2. So let's do that. Let's take F over 2. Let me turn off the video. I don't think we need the video. It's just clogging up the screen. Give me a second here. See if I can figure that out. Okay, there we go. I think that's good. I think you can still see my screen. Well, I'll make sure of that before I upload this video, but my guess is yes. Okay. All right. So, all right. So we're gonna take the 2 over F root. Right? So I want to get rid of that F over 2. So I'm gonna take the 2 over F root of everything. Now, when I take the 2 over F root of the constant, it doesn't matter, it's still a constant, doesn't matter what, right? It's like constant or constant squared. God, this is ridiculous. Hold on, I'm gonna close the door. This is just ridiculous. Hold on. All right. Better. All right. All right, so when I take the 2 over F root of the constant, it doesn't matter, right? It's just a constant. Okay, so let's put everything to the 2 over F root. So what that does is that's going to give me V. So this is 2 over F, should be in that little square root place right there, right? Okay, so that's going to give me V. And then the PV over NK, this is all under the root still. F over 2 is equal to just a constant, right? Doesn't matter that I had to take it to the 2 over F root, doesn't matter at all. Okay, now the 2 over F root is going to cancel this 2 over F root here, right? But it's going to give me a V to the 2 over F root. So V to the 2 over F, right? Yeah, that's how that works. And then PV over NK, that gets rid of the 2 over F, or sorry, the F over 2, and it's still all equal to a constant. All right, now, if I combine these two V's, right, what do I have? I have the P, I'm going to put the P over here, over NK, and then I combine the two V's, and I have V, but now it's to the 1 plus 2 over F, right? And all that's equal to a constant. And also, I can take that NK, which is a constant as well, and multiply it times my constant, so I can sort of get rid of it, right? It's all just incorporated into that constant. So coming up here, we have V to the 2 over F plus 1 times P is equal to a constant again, right? It's just a different constant. Okay. Now, I can rewrite this as V to the 2 plus F over F times P equal a constant. And I can rewrite one more time, V to the gamma P equal a constant. Okay, where gamma is called the adiabatic index. And it's equal to that 2 plus F over F. Yeah, and as you can see, that adiabatic index really only it only has the degrees of freedom in it, really. That the only thing that's relevant to what kind of molecule it is, as we saw before. So, and we can kind of see that the the energy that we're liberating, right, to expand or compress, liberating or that's required to expand or compress the gas is really coming from the degrees of freedom, right? From the energy of the internal energy of the molecules themselves. Okay. So if we drew this, right, we would, let's draw these processes. All right, so let me get another layer here. Okay, so now, so if I draw it here on a PV diagram, so we have V and we have P. Okay, and then let's draw 2 isotherms. Now we never really drew the isotherms, but they kind of look like these nice curves. So let's say we're starting from here. Let's say we start from P4 and we're going down to P1 or let's see, P3. So an isotherm looks like, oh, I better say where we're going, V1 and V2 as well. So let me do that. I'm sorry. Let's put that on here too. So we have V1 and V2. Okay. So for an isotherm, it's kind of a curve and it's kind of hard to draw. So I'm going to draw these little dotted lines that'll help me draw here. So an isotherm is kind of like an, oh boy, it's very hard for me to draw. So it's kind of a nice curve, okay? Oh, I needed this line too, so I messed that up when I get that better, okay. So there we go. It's kind of a curvy line. It's not a, I'm sorry, it's a curve, it's not a line. Okay, and then we have, let's do another isotherm that goes from P2 to P1. Okay, and we'll do another isotherm that goes, yeah, from P2. So let's go here to here. There we go. So that's another isotherm. So an adiabat, right, is actually connects to isotherms, right? Because we go from one temperature to another temperature. So if we think of an adiabat as say we're doing compression, right? We come up from one isotherm to the next, right? Okay, just so you know what it kind of looks like. All right. All right, I think that's all we need to do for the adiabat. Just so you know that when are things adiabatic? Okay, so we talked about how processes should be slow so that so that I can still call the pressure inside the gas the external pressure. But it turns out that slow in quotes can mean can even mean fast enough so that the heat doesn't escape or come in, right? So in some sense, adiabats are fast enough that heat doesn't escape or have to come in, right? Or come in from the environment, but not so fast that it's not a reversible process, right? We talked about that. Okay, so it's still slow in quotes, just fast enough so that you don't have heat exchange with the environment. Okay, let's move on from that, and you'll get some more practice on your homeworks. And we'll go on to section 1.6. Okay, this is all about heat capacities. Let me get a new layer. All right. Okay. Okay, so heat capacity. And there's still noise in here, by the way, because these walls are made of paper. Capacity, sorry, my bad. Okay, so what's the heat capacity? It's the amount of heat needed to raise temp. So you can write, and you've probably seen this before in elementary physics, C is just defined, so this is the heat capacity, okay, right here. It's defined as the amount of heat you need to change your temperature by delta T, right? And it's in units of the heat per degree or energy per degree. But the more of a substance you have, right, then the more heat you need. So really specific heat is another constant. Well, another quantity, it's not constant, sorry, quantity. So this is the specific heat capacity. Okay, and that has the mass in it as well. It's just defined as the regular heat capacity over M, right? So it makes sense that you need the mass in there because of how much of this of the substance there is makes a difference in how much heat you got to put in to raise the temperature, right? Okay. Now, just to be clear here, right? The amount of heat, as you already know, that you need to raise the temperature really depends on if you're doing work, right? By the first law of thermodynamics. So, you know, if we write this out, let's go back to here. We just write this out and say, well, okay, this is delta U minus W, right? If you remember that, from the first law, delta T, this work can be anything. So this gets a little ambiguous, and so we're gonna try to tack it down. Okay, all right, but we can, because we can break down that work into kind of like two things that we've already talked about, right? At least two. Okay. So first of all, if the work is zero, so let's say there is no work being done on the system or by the system. I know I don't have my video on because my camera is completely in the wrong place. Anyway, I don't really think you need to see me, but when you have no work, so let's do that case first. So let's do case one, in which work is zero. Okay, case one, work W equals zero, which implies that delta V is equal to zero, right? That's what it implies. So the volume is a constant. Okay, well, we can define a heat capacity in that case, right? Because we know in that case, W is zero, and we just say, look, let's get a heat capacity in the case where W is zero. And it turns out it's a very simple formula, and it's the heat capacity at constant volume, that's what that V means. And it's defined as the change in the energy over delta T. Well, you can look at that formula above and see that, right? Because W is zero, but this is a reminder. And it's really nice that you can actually use this in derivative form. That's a partial derivative, by the way. And this means at constant volume. So for instance, we know that U is a function of T, right? So U is F over 2 NKT, right? So partial U, partial T would just be the derivative, which would be F over 2 NK, right? Very simple. Now, the energy may not be that particular function of T if your energy is not all coming from quadratic sources. Remember that's when we can use that equipartition theorem. But in general, right, it's this derivative. So you can get the specific heat, the energy capacity, as people call it, which is just the specific heat at constant volume. Okay, fine. The other case, of course, is where you have work being done, but let's narrow it down. Okay, so get another layer. Okay, so for case 2, let's do that in green. So case 2, okay, and this, to be honest, like if you think about doing things at constant volume, that's not the most relevant for kind of everyday life, right? If you think about heating up a gas or well, yeah, heating up a gas in a tank or something, it's going to expand, right? So it's not a constant volume. It's a little artificial and it's not as useful as this next thing. So in everyday objects, things expand, right? When they're heated, etc. The object would do work on the environment. So let's take that case, right? So let's look at, in general, non-zero W, okay? And in general, let's look at when the W is less than 0, right? The object is doing work on the environment, and we'll write our heat capacity like this, equal delta U plus, and then the absolute value of the work. We know it's negative, right? And so we can write that down. Remember, we had a negative sign on that previous equation. If you roll back the video, you'll see, okay, over delta T. Okay, now this is always greater than CV, right? You notice, because it's got that W, absolute value W over delta T. Okay, so great. Let me see if I can move my camera, because if I can move my camera, it might be better. It's funny, I feel like I really do need to have the video on to communicate correctly, which is kind of dumb, but that's kind of what it feels like. All right, let's see. Let's get the video on. Boom. Oh yeah, I have to go up here. Give me a second here. Let's try that. Hello? Okay, that's a little better. Okay, at least I can kind of see what's going on. All right. It makes me feel a little bit more comfortable. I'll try not to get that in the way. All right. Okay, so you have to put in extra energy to compensate for the work done. Hope that makes sense, to change the temperature, right? That's what we're after. Like, how much energy do you have to put in to change the temperature? Well, I got to put a little extra because you're doing some work on the environment. Okay, so what usually is constant in these situations is actually the pressure. So if you think about, I don't know, getting water going into steam, becoming steam, and you heating up the steam, like superheating the steam, right? It's going to expand. You're usually, if you were doing that in, in an experiment in a lab, most likely the pressure would be the same between all the things that you're doing, right? It would be atmospheric pressure. So in general, like, constant pressure is a lot more useful, okay? So we can define the specific heat. So this is specific heat at constant pressure. Okay, and that is just, well, from the formula above, basically, right? We put delta U and then minus the PdV, right? So now I'm being a little bit more general, right? Here, up here, we were just trying to make a point about the fact that it's greater than CV. Okay, so now I'm being more general, writing down the general formula for work, right? And then over delta T. Okay, and this makes sure that I know this is at constant P. And again, I can write this in terms of partial derivatives, right? So I can write this as partial U, partial T, and to say, be careful, this is a constant P. That's what a partial derivative means, but just to be very clear. And then plus P, partial V, partial T, at constant P, okay? So now we have a formula where you can take the derivative of two things and get your specific heat. Now, if you have solids or liquids and this is what you're applying this to, right? Well, or you're trying to figure out how much heat do I need to change the temperature of a liquid. This dV, right? Liquids don't really expand when you heat them, right? Gases do. Solids a little. Sure, but in general, this might be a very small term, right? So it maybe could be ignored, but that's really valuable, right? Okay. All right. So if we wanted to predict what the specific heat was for things that we know, follow the equipartition theorem, that means that we're only considering the quadratic forms of energy for this, whatever this is, a gas, let's say, right? Like a ideal gas, then we know what U is, right? We know that U is equal to 1/2 N times the number of degrees of freedom times K times T, right? And so I can certainly now, let me go back to my other color. Let me see, what color did I put? Pink, yeah. Okay, so now let me go to pink for the, we're gonna do CV now, because so CV, that's easy, because I know that CV is partial U, partial T at constant volume, right? And that is easy for this term, like I told you, I sort of spelled it out when I was just talking about it. This would be NFK over 2, right? I'm just taking the derivative of this with respect to T. So that's really great. Now, is that really what it is for certain gases? Yeah, it's pretty close, okay? So like for instance, in a helium gas, like we talked about before, that's just monatomic. We expect that to have 3 degrees of freedom, right? And we expect that our CV, so for helium, F equals 3, and we expect that our CV is going to be 3/2 NK. And I can rewrite that as 3/2 NR, right? And that turns out to be about 12.5 joules per Kelvin. So you need to put in 12.5 joules for every degree Kelvin you would like to heat up this gas, right? And if you go look that up, that's what the prediction is, what the measured value is. Okay, let's just take a look at a nice plot of what we might expect for a diatomic molecule like H2. Right? We talked about H2, we have 2 hydrogen molecules, and I'm looking up at my light instead of the camera, my bad. Anyway, 2 molecules, H2, and they're bonded together, right? So let's look at a plot at CV at different temperatures. Because like I told you before, sometimes you're not able to, that molecule is not able to access all of its degrees of freedom. And we can measure CV, and that will tell us how many degrees of freedom that thing can access at different temperatures. Okay, so let's take a look at a plot of that. Okay, so this is just CV now, okay? All right, so let's plot. So we're gonna do CV, and then we're going to do the temperature in Kelvin. My bad. Kelvin. Okay, there we go. Okay, so let's go down here. We'll have a low 10 degrees Kelvin, and we'll put 100 right here, degrees Kelvin. Getting closer to kind of normal temperatures, 1,000, which is quite high. Right, remember room temperatures right here at 300 somewhere, right? And then we're just going up. All right, let's take a look at CV, at what we measure, okay? And these are approximate, right? So I'm writing down the exact values that we predict, but they're approximately true. So in other words, think of these as measurements. All right, so we have one here where we just have the translational degrees of freedom, right? That gives me 3/2 NR, right? So 3/2. Okay. And the translational degrees of freedom, so that would be at low temperatures, the only thing available to that gas are the translational degrees of freedom. So I'm going to plot that in pink here. So if we go here, like I'm just doing, this dotted line means, well, I guess I should make it a solid line, but maybe make it a dotted line. The dotted line means that this is very hard to measure at these low temperatures. Okay. But even all the way up to 100, right? You're just not accessing anything else. So the CV is what you would predict for only having translational modes. This is what I was talking about before about being frozen out, right? Some modes, some energy types are frozen out, frozen, meaning it's too cold for them to be excited and be able to access those modes of energy. And so let's go to, let's put in 5 halves. And this is rotation. Remember, we talked about how if you have a diatomic molecule, it can rotate like this. So think about it, this is the y-axis, rotates around the y-axis, rotates like this around the x-axis, but cannot rotate, cannot rotate about itself, basically. So that's the only 2 it's got. So it's got 2 more degrees of freedom when it's able to rotate. Okay, so that kind of shoots up to 5. So that should be pink, my bad. So that shoots up to about 5 halves, right? So we added a couple degrees of freedom. And it's not till you get to about 1,000 where you start getting that vibration, or you start heading your way up to vibrations. We talked about how it might have, 1 or 2 modes of vibration. So in fact, 2 is the kind of highest it can have. And if we make a dotted line out here, it doesn't quite get there. It's heading its way up, right? When we get close to 1,000, that's when it starts to head up. Starts heading its way up towards its maximum, right? So if you measure the specific heat at constant volume for a diatomic hydrogen, right, you'll see at different temperatures that it has different values, and it's exactly because of the equipartition theorem and the fact that some modes are just not available for this. Some energy modes, right, are not available for the molecules. Okay. All right. Let's see what else we got. All right. So let's look at the constant pressure one, right? That was in green. Okay. So remember that for the constant pressure, right? We know that, so this is the heat capacity. At constant pressure. Not gonna make a plot, but I'm gonna try to do some predictions. Pressure for ideal gas, with only quadratic forms of energy that we're considering, right? With only quadratic forms of energy, quadratic forms of energy. Okay, so remember that CP, constant pressure is partial U, partial T. Okay, we already know how to do that at constant pressure, plus P, partial V, partial T at constant pressure. Okay, so how do we do that? Okay, fine. So I'm gonna, first the U, that's very simple, right? We already know how to do the partial U, partial T. Doesn't even matter that it's a constant pressure here, right? Because U is, remember that U is 1/2 F N K T, or if you want it in terms of N and little n and R, but we'll keep it in NK. So the partial U, partial T, of course, is just F over 2 times NK. Okay, that's easy. But then we got this guy, right? Well, but I already know what volume is for an ideal gas, right? From PV equals nRT, I get NKT over P, right? So think about what is partial V, partial T, okay, at constant pressure. All right, so I'm going to write that down. I'm going to put that V in here. So this V here, so I have partial T, and then the V is NKT over P, but I am told to leave P as a constant, right? So I'm going to come over here. I'm kind of out of room there, but let's partial V, partial T at constant pressure. And that P on the bottom doesn't factor into this derivative at all. So we literally just get NK K over P, right? Okay, let's put it all together. I'm gonna use another layer. And I'm gonna erase this top part. Right. And I'm gonna erase all this down because we have some of the stuff already. Okay, so CP again for our ideal gas with only quadratic degrees of freedom. We have partial U, partial T at constant pressure. At constant pressure, we know what that is. It's F over 2 times NK. And then we have the partial V, well, P times partial V, partial T. So we have plus P, and then the partial V, partial T becomes NK over P, and those P's cancel out, and we end up with F over 2 NK plus NK. And I want you to notice here that this F over 2 NK is actually the constant, the heat capacity at constant volume. And then we just add in the NK, right? Or if you prefer, instead of NK, we add in the number of moles times the Rydberg constant, NR. So we add NR instead, if you want that, if you like that better. But notice, again, greater than CV as promised. Of course, it has to be, right? Okay. So now let's talk about something called well, actually, let me write down one more thing. Okay. Just as a note, right? If you go up here to this equation, you can see that this is F over 2 plus 1 times NK, right? So given the degrees of freedom, you already know what CP is, right? As we also know what CB is, but we have to be careful about the fact in general that not all degrees of freedom are accessed at all temperatures. Okay. Let's talk about something a little different. Okay, so I think you're all aware that there are times when you're adding heat into a system, but the temperature is not changing, right? So how do we account for that? Given that we, CV and CP are all for changing temperature. If delta T is 0, then you've got an infinite heat capacity, right? Okay, so what am I talking about? What situation am I talking about that you all know of? Imagine that you put on your tea kettle, right? So what's happening in your tea kettle? You are pumping energy in, or how about we think about just a pot of water for boiling for pasta because you can see the boiling, right? If you've now turned on the water, you wait for a while and your water starts boiling, it's going to keep boiling, right? Unless you turn the heat down. You're pumping heat in, but boiling water has a temperature of 100 degrees Celsius. It is not changing temperature. What is happening is water is being turned into water vapor or steam, and eventually it'll all get turned into steam and you'll burn your pot, right? So we're pumping heat in, but we're not changing the temperature, okay? So we have to think about what's going on there and how do we kind of get a handle on that? Because obviously we are putting heat in, right? And the more heat we put in, the more mass we have, the more water you have in your pot, the more heat you got to pump in, right? So, and yeah, I know that you've seen this before somewhere, probably in physics 2 or physics 1116. You've probably seen this idea of latent heat. So let's talk about latent heat. Okay, this is the amount of heat that you have to put into something to change the phase from, say, water to steam, or from water to ice, etc. Okay, it's also a little ambiguous, but we're going to ambiguous in the same way the CV was, or sorry, the heat capacity was, because we have to make sure we understand what conditions we're under. But in general, we really are only going to talk about, and we're not really going to talk about latent heat much. I just want to point it out. We're only talking about at constant pressure, right? I mean, that's what's happening when you're boiling your water on the pot, on the stove. I mean, right? It's constant pressure, it's atmospheric pressure. So we are just going to assume that that's the situation that we're in. Okay. And the latent heat is just defined as the Q over M. And this is really depending on what you're changing. There's a latent heat of fusion and a latent heat of vaporization. We don't use this as much in this class, but it's good to know that that's what's happening, right? Because it can be confusing if you start thinking about specific heat in the way that we've been thinking about it, and you realize there are times when you pump a bunch of heat into something, but that heat is not going to raise the temperature, it's going to changing phase. Or you take a lot of heat away when you freeze something. Okay. Anyway, all right. Let's move on to something called enthalpy. And this is kind of a strange duck, I gotta say, but it is useful, especially for chemists. Okay. So let's talk about enthalpy. Okay. So constant pressure is so common, right? It is so common that it would be really useful to not have to keep track of all that work that we're doing, right? Because remember, when you have constant pressure, you got to account for the work that's happening, right? To keep something to constant pressure, you're going to have volume change, and you got to keep track of all the expansion or compression work that you're doing. It would be nice to not have to deal with that, and enthalpy does help with that. It is a little bit hard to understand, but let's say we can get a handle on it. Again, we're not going to use it that much, but it's good to know what it is because you do hear it. All right, so let's imagine a system. So we have a system that is going that goes from this pressure. So we're going to go at this pressure is going to stay constant. So we're going to stay at that pressure, but we're changing our temperature and we're changing our volume, right? Again, right? We're changing the pressure, which means we're putting in some heat, and the work is going to be non-zero because we're actually going to change the volume as well, right? We're in the constant pressure situation, so pressure doesn't change. And we go to a new temperature and a new volume. Okay, we're not saying whether one's bigger than the other. We of course know that the U, delta U from our first law is Q. Remember, that's always delta Q plus W, and we can write that as Q minus P delta V, right? Like we've done before. And we're always thinking about reversible processes, right? Okay. So now I'm going to pull that P delta V over to the other side. So I have delta U plus P delta V. Okay, remember that P is a constant. So what that means is that and I'll put the heat over here. So the idea here is let's keep track of the heat. Let's get the heat without having to keep track of all the work, the compression work that we're doing. All right. So because P is a constant, I can pull that delta out and use this as U plus PV, right? And that's Q, okay? And remember, this is the heat, Q is the heat going in or coming out of the system, right? Okay, which is what we're interested in. And so what we can do is define a quantity called the enthalpy. And we usually call that H. And by the way, that is not very standard, so FYI, okay. So where H is this thing called the enthalpy. So H is U plus PV. Okay, all right, fine. And you can see that the change in the enthalpy is that heat that you're after, okay? This changes in enthalpy are caused by heat and not by compression work. It's all built into that enthalpy, right? So let's see how that's all related to our CP, right? Okay, so let me go to a new layer. Let's see, what layer are we on here? Let's see, equivalent layer. Okay, perfect. Okay, oops, no, I meant to copy that layer. My bad. All right, did I mess this all up now? Yes and no, let me fix it. Okay. Yes, okay, should be able to erase now. Let's see if we're good. Okay, fine. So now I have enthalpy. I'm gonna erase this latent heat stuff. Okay, so let's see how the specific heats that we were working on are related to the enthalpy. I hope you can see that it actually is going to be helpful, or maybe you don't see it yet. Okay. Let's look at the heat capacity at constant pressure. Okay, Cp. Remember, that is partial U, partial T at constant pressure, plus pressure times partial V, change in volume at constant P, sorry, change in volume with temperature at constant P. Now notice though, I can pull out, because P is constant, I can pull out this derivative with respect to T out of the whole thing. So U plus PV, because P is constant, and I still need my little P there to tell me that it's constant. And that is just the derivative of the enthalpy. Right, at constant pressure. Okay, so that's really nice. And it tells us something, how to get Cp if we know the enthalpy. Okay. Let's do an example, and hopefully it'll be clear that it's a little helpful. Okay. All right, so let's do our example here. Let's say we're boiling 1 mole of water into steam. Now we know that there's going to be some expansion, right? You start with a little bit of water and you boil it into steam, you're going to have a much bigger volume of steam than you did of the original water. Okay. We can look up the enthalpy, okay, of this process. And so we can say this is actually 40,660 joules, okay? And it's positive because heat's got to go in to this process. Okay, so let's take a look. So we know that the original volume is approximately 0. So say you just have, 1 mole of water is not very much water. And we're at 1 atmosphere of pressure. Okay, and then we go to some other volume of steam, bigger volume of steam at volume V. Okay, so we're going from basically 0 to V. That tells me what delta V is, right? Because the delta V is V final, which is my big V there, minus V initial, which is 0. So this whole thing is just V final, which we said was V, okay? And what about delta U? Okay, delta U is Q minus P delta V. Okay, so that's Q minus PV. Yeah. And the enthalpy Q is also delta H, which remember H is U plus PV. So we have delta U plus P delta V, but delta V as we see is just V. So we have delta U plus PV. Okay, cool. And so the energy, the enthalpy is the energy needed to change phase plus the energy to make room for the steam, okay? Because you have to make room for that volume V. Okay, so again, we're not going to do that much with the enthalpy in this class, but it's good to know what it can be used for. Remember that it's used in the situation, the very common situation of having constant pressure. But again, we don't use it this much. It is very highly used by chemists. And I don't think we're going to see it again. We'll see it maybe on homework, but definitely not in the rest of the class. Okay, but it's good to know what it is. All right. That's all I have for you. Let me turn off the share. Let me turn off the, there we go. Let me see if I can. All right, we'll see you in class.